Okay, so we will start now. ठीक है. So today we are going to start with the new topic that is the design of pump house. Okay, so uh, this is a typical cross section of pump house. So I want everybody to draw this figure. So here you can see there are different components of RCC structure. Like there is a roof slab. Okay, so we will be designing this roof slab. Then there is a roof ring beam. Then we have column. Brick wall is just for a partition, so it has to be taken care while doing the load calculation. Then we have to design the RCC gantry girder plus the corbel. Then floor slab is there. Then walkway is there. Some floor beams are also there, and there is a jackway. Okay, so the pump house consists of all the components except jackwell. So jackwell has to be designed separately along with its foundation. But pump house has got different components. Okay, so you can see that there are these many components. Okay, so please draw this figure very neatly, and this is the problem statement which is given to us, that we have to design this pump house with the internal diameter as 6 meters. Okay, then the height of the pump house is given to you as 6 meters. The supporting columns are 6, and SBC is 100, and we are assuming M25 and Fe415 grade steel. Okay, so please draw this figure. So here you need to understand there is a steel girder. You can see the steel girder over here. So this is basically this is basically steel girder. Okay, so this girder is resting on this rail. Okay, so you can see this is the rail section uh, which is over here. Okay, so this is the rail section, and the rail section is resting on the gantry girder. So gantry girder will be circular in nature. Okay, so accordingly we have to design it. And apart from that, you can see there is a pump over here. Okay, so the pump is resting on the floor beams, so we have to design floor beams as well for the applied load. Yes, is it done? Shall I continue? सिर्फ स्केच बनाओ, एकदम पूरा एज इट इज ड्राइंग मत बनाओ, ठीक है? दिस इज जस्ट अ स्कीमेटिक ड्राइंग. Shall I continue? Yes, shall I continue? कितने लोगों का हो गया है? Just one, two, three, four. I think we can continue. I am going to upload this figure in the Google Classroom. GSR design has I have already uploaded yesterday. Okay, in form of a PDF. Okay. So anyway, we'll move ahead. So this is the problem statement. That is the internal diameter is 6 meters. The height is 6 meters. 6 columns. SBC is given. FE415 and M25 grade concrete is given. Okay. So now for the design of RCC structure using working stress method, you need to find out the design constants. Okay. So sigma CBC for M25 grade concrete is 8.5. Sigma ST, that is stress in steel, for Fe415 is 130. Accordingly, you please calculate the modular ratio M, K, J, and Q, and please tell me the values. M value, I think it is 10.98, I suppose. Check karo. How much is this? So this is 280 divided by 3 times 8.5. कितना है? 10.98. Okay. What about K? So this is 1 upon 1 plus sigma st is 130 divided by m is 10.98 multiplied by sigma cbc is 8.5. How much is this? Sorry, 0.0418. Okay. This is 1 minus 0.418 divided by 3. कितना आ रहा है? 0.86. And how about this one? Sigma CBC is 8.5, okay, divided by 2 into 0.86 multiplied by K is 0.418. बराबर है? What about Q value? 1.5. Okay, so this is 1.527. Okay, so these are the design constants, and these constants will be needing in the further design calculations. Okay, so today we will try to finish two different components RCC design. So the first is the design of roof slab. Okay, yes, is it okay? The simple calculation. Okay. So let us start with the design of roof slab. So remember, in the GSR we have gone for roof dome. Okay. So the roof dome and roof slab you can provide in the GSR also, as well as in your pump house also. Okay. So in previous class we have seen the roof dome along with the ring beam. Here today we will see the roof slab along with the ring beam. Okay, so it's a combo actually. So if you are providing the roof dome, the corresponding beam has to be designed for tension. But if you are designing this roof slab, then we have to design the ring beam for the bending moment. Okay, so here what we are going to do is, first of all, we are going to assume the thickness of the slab. Okay, so thickness of the slab can be assumed based on your experience. So this is a 6 meter span, so definitely 100 will not be sufficient. You may have to go for higher one. So to be on higher side, we are going for 200 thick slab. And the width of the support, so at this point you need to define how much will be the width of the beam. So the beam which is shown in dark black, solid black color, it is nothing but a beam and it is running throughout its periphery. So the slab is resting on that beam. So at this moment itself we have to define how much will be the width of the beam. So we are assuming that the width of the beam is also 200 Okay. So now based on this assumption, now let us do the calculation. The very first thing is the load calculation. So load calculation, it's basically the self-weight of the slab. So the thickness we have already assumed this as 0.2 meters, okay, multiplied by density of concrete is 25. So this gives you 5 kilonewton per meter square is the dead load of the slab. Okay. Now based on the IS code, we have to take the live load. Okay, so the live load, the bare minimum value is 1.5, and floor finish is an optional thing. So in your actual structure, if you are providing any kind of coating, okay, so that load has to be counted over here. So I'm assuming the floor finish as 0.5 kilonewtons per meter square. So the total UDL which will be coming on the slab will be 5 plus 1.5, that is I think 6.5, plus 0.5, that comes out to be 7. Okay, so the total load which is coming over here, it is 7 kilonewton per meter square. So you can see on this slab there will be a UDL which is like this. Okay, so this UDL will be 7 kilonewton per meter square. Okay, now remember, this is not a simply supported beam, this is a circular slab. Okay, this is not a beam, although in the section it looks like beam, but it is a circular slab, and the circular slab is supported throughout its periphery. Okay, so there will be a different coefficient for the maximum bending moment. Usually if you take a simply supported beam, so the maximum bending moment will be w WL square by 8, okay, if it is a simply supported beam. Okay, and it is WL square by 12 if it is a fixed beam. Okay, but this is a circular slab, right? So for this there is a equation which is very much similar to your fixed simply supported beam. But before going for that, we have to find out the effective length or the effective diameter of the slab. So the clear diameter is basically 6 meters. Okay, so here this is nothing but 6 meters. So half of the width of the beam which will be over here, and half of the width of the beam will be over here. So half of the width of the beam, this will be 0.1, this will be also 0.1. So the effective diameter of the slab will be nothing but 6.2 meters. Okay, and the effective radius, so effective radius of the slab will be now exactly half of that. So this value will be something like 3.1 meter. I hope this is clear to everybody. Okay, so now with this, let us calculate the bending moment. So here the bending moment equation for the circular slab subjected to UDL is W into effective R, that is radius effective square, divided by 8. So your load, so load value we have calculated this as 7 kilonewton per meter square, and effective R, that is radius, effective radius is 3.1 square, okay, divided by 8. Okay, so this looks very much similar to your simply supported beam subjected to UDL. Okay, so how much is this? Someone please tell me. Sorry, 8.41. Someone please verify. 8.41 kilonewton meter. Okay, so this is the effective bending moment or the maximum bending moment in the slab. So now we have to design the slab using the working stress method, And while designing the slab in working stress method, what we do is maximum moment is considered same as the moment of resistance. Okay, and the equation for moment of resistance can be calculated by a simple expression Q BD square. Okay, so if you expand this expression, okay, so if you expand this expression, what you are going to get, so maximum bending moment is 8.41 into 10 to the power 6, okay, equals to Q. Just now we have calculated the value of Q as 1.527, okay, that is 1.527 into width. So since this is a slab, so width has to be taken as 1000 mm multiplied by d square. So from this you can get the value of d. How much is the value of d? Someone please tell me. Sorry, 74 point 74.2 जो भी है, okay, let us 75. Okay, so this is the effective depth, so definitely we have to add the effective cover. So effective cover is half of the diameter of the bar plus the clear cover. Okay, so if you assume the clear cover as 20 mm and the diameter of the bar as 10 mm, so that becomes effective cover becomes 25. So from this, so let us say this is 25 mm, so this will be 75 mm. So the depth which is required over here, this is going to become 100 mm. ठीक है, so 100 mm is sufficient. We have assumed almost the double of the uh, actual depth which is required. Okay, so definitely we can revise this. So in place of assuming 200 mm, if you assume 100 mm, तो तुम्हारा डेड लोड जो है वो वैसे ही कम हो जाएगा. सो डेड लोड कम हो जाएगा तो बेंडिंग मोमेंट भी कम हो जाएगा. सो आई एम श्योर 100 mm will be sufficient. Okay, but still just we will continue with the same values, but in actual practice you have to reduce the depth and you have to redesign it. Okay, so let us assume the 200 mm itself over here, and let us see how the design is going to be there. So if you take the effective depth or the total depth as, let us say, 200 mm, okay, for example, so the effective depth will be 200 minus 25, so that is going to become 175 millimeter, and AST can be calculated as the maximum bending moment. So the maximum bending moment right now it is 8.41 into 10 to the power 6. Sigma ST is 130. J, the value of J, I think it is 0.86. So this is 0.86 multiplied by D is now 175. So how much is the area of the steel which is required? कितना आ रहा है? 429. Can I make it 430? 430 millimeter square. And if you take a minimum AST, that is 0.24% of the cross section area. So this is 0.24 divided by 100. Cross section area will be, total depth is 200 into 1000. So this becomes something like 480. बराबर है 24 का डबल. Okay, so you can see the AST which is required, it is less, and AST minimum is more. Okay, so in this case we have to provide the which value? AST minimum value, of course. So AST minimum, if you take 480 millimeter square, can you calculate how much is the spacing of bar which is required for 8 mm dia bar as well as 10 mm dia bars? So if you provide 8 dia bars at 104 millimeter, बराबर है. So if you provide 8 mm dia bars, you have to provide the spacing at 100 mm center to center. So now since this is a minimum reinforcement, it has to be provided on both the sides. Okay, so either you can provide in form of a square mesh, okay, or you can provide it in form of a radial and circumferential direction reinforcement also. But in both cases, you have to provide the bars at 100 center to center. And please observe this drawing very carefully, because some of the bars they are bent and they have taken to the negative side, especially above the supports. Okay, why it is done? Anybody? Why these bars are bent like this? ये वाले bar. The main bars they have taken up. This is a simply supported beam or simply supported slab, but still some portion of the main reinforcement has been taken up. For negative bending moment if anything comes up. Okay, so in that case the topmost portion, especially above the support, it may be subjected to tension. So because of that we have to take some bars. Generally what we do is half of the main reinforcement is provided at the top, they are just turned up, and it is provided up to a certain length. Okay, so this part you have to remember, and this completes the simple slab design. Okay, so this is simple circular slab, there is no as such shear is coming into picture over here. Okay, if you calculate the shears, definitely in all the slabs the shear reinforcement is not at all required. Okay, because it is always shape in shear, but still if you want you can go for check for shear also. Okay, so this completes the design of roof slab. Okay, so let us continue further, and let us quickly check the next part, that is the design of roof ring beam. Okay, now you can see in this picture there is a house, and it's a kind of a veranda. It's a circular or semicircle in shape, and above that you can see there is a slab. Okay, so that slab is resting on a circular beam, right? We can see only the half of the circle, so it's a semicircular beam, and that semicircular beam is supported by the column, right? So this is the exact scenario which we are facing over here. So the slab is resting on the beam and the beam is resting on the column. So here in the problem statement itself, it has been given that this is a circular beam and it is rested or it is supported by 6 number of columns. Okay, remember it is supported by 6 number of columns. So we have to design this as a circular beam. There is a separate chapter for design of circular beam in Krishna Raju book, which I have already shared, I suppose, in the Google Classroom. So please go through that. Okay, it gives you a very detailed design. Right now what we are doing, we are going for preliminary design because it's not that much heavily loaded. Okay, but whenever we are going for the ends time design, in that case it will be very heavily loaded and all the criteria will come into picture. Okay, so anyway, so this is the situation. Now for this purpose, first of all we need to calculate some dimensions. So right now we are assuming the circular beam which is resting, which is supporting the slab. We are assuming the dimensions as the beam size. Width we have already defined as 200 mm. Depth I am assuming this as 400 mm. Okay. So now if I take this, the average diameter of this circular ring beam will be same as the average diameter of the slab. So this will be clear diameter. So clear diameter is nothing but your 6. Half of the width is nothing but zero point 0.1 and half of the width is nothing but zero point 0.1. So the average diameter becomes 6.2 meters. Okay. So now if this is 6.2 meters, so what will be the length of the curved beam? So length of the curved beam, so if you open the curved beam, it will become a straight line. And that straight line is nothing but the perimeter of the beam. So perimeter of the beam can be calculated by a simple expression pi into d. So where d is nothing but your 6.2. So how much is this length? So the total length of the circular beam, sorry, 19.47 meters. Okay, so now this beam is supported by 6 number of columns. Okay, so here if you substitute the value of L as 19.47 and number of columns at 6, how much will be the length of single span in curve? 3.24 meters. Okay, so this is nothing but 3.24 meters. Okay, so the single span which is curved in plan, so distance between two supports is 3.24 meters. Okay, it is quite large, roughly 11-12 foot. Okay, so we have to design this particular beam now. So now for this purpose, first of all, we have to do the load calculations. So now you see we have already calculated the load which is coming on the slab. Okay, slab was consisting of dead load, live load, floor finish, and the total load was coming out to be 7. Okay, so the this total load on the slab, this was 7 meters. Okay, sorry, 7 uh, kilonewton per meter. बराबर है? Then if we multiply with the exposed area, okay, so the exposed area will be pi by 4 into d square, where d will be your d outer now, that is 6 meters, which is clear inside, point 2 this side and point 2 other side. So here this value will be pi by 4 into d will be 6 plus point 2 plus point 2 whole square. So how much is the total weight of the slab, which is inclusive of self weight, floor finish plus live load? बताओ भाई. Sorry, 225.19. Somebody cross check. Okay, so this is 225.19. This will be in kilonewtons because this is a total load. Okay, now this load will be distributed along the length of the beam. So if you divide this with the length of the beam, what you are going to get is the UDM. Okay, so anyway, but before going for that, we have to calculate the self weight of the beam. So we have already decided the dimensions of the beam. So B is 0.2. Okay, depth we have considered this as 0.4, and the total or the effective diameter. Okay, so effective diameter, I think it is 6.2. This we have already calculated in the previous slide, and the density of concrete is 25. So how much is the self weight of the beam? This will be also in kilonewtons, that is the total load. So area into length into density of the concrete. How much is this? 38.96. Anyone? Yes. So this is 38.96 kilonewton. So the total load will be 225.19 plus 38.96. How much is this? Someone please tell me this value. कितना आ रहा है? 264.15. So this is the total load. Okay. Now this total load will be acting throughout the periphery of the curved beam. Okay. So if you divide this with the length of the beam, what you are going to get is the UDL on the beam. Okay. So all we have to do is just divide this with the length of the beam. So this will be 264.15, and the total length of the beam. So total length of the beam we have already calculated this as 19.47. Okay, so this is 19.47. So this is nothing but a UDL. How much is the UDL? 38.13. Okay, so this is 13.56. This will be kilonewton per meter. बराबर है? ठीक है? So now always remember there are two W's. One is capital W. Okay, so capital W is the total weight in kilonewton, and there is a small w. So small w is UDL. Okay, so with both the w's, now we are going for the further calculations. Okay, so now you see this is a typical figure which is showing a beam which is curved in plan. So on the right hand side you can see there is a circular beam. Okay, it is supported by 8 columns. Okay, on the left hand side you will find some section is drawn, right? So here if you see, here I have, this is a support over here. Okay, and there is a support over here. So wherever there is a support, you will find there is a negative bending moment. Okay, and at the center you will find, at this location you are going to get the positive bending moment. Okay, maximum positive bending moment. So if I draw a typical bending moment diagram, it will look like this. So it will have some negative bending moment over here, it will come down and then it will go up. So here you have the positive and here you have negative, right? Now since this is curved in nature, you will have a torsion also. So this is the point. Okay, this is the point where you will find the section which is like this, it is going like this. Okay, but due to load it will turn, right? So if it is going like this, so while going like this it will also turn, and the maximum torsion will occur at that particular points. So this angle is there, this is the beta, it is measured from the support. So at this point you will find the maximum torsion, and whenever there is a maximum torsion at that point you will have a added bending moment. Okay, and for this added bending moment you have to go for the design, or you have to provide the additional reinforcement. Okay, so this is the simple explanation of the design of curved beam. And this particular figure you will also find in any of the standard RCC book where the curved beam is explained. And here there are some expression. So this is the first expression. Okay, this is the first expression. It says the negative bending moment in the beam. So the negative bending moment in the beam can be calculated by simple expression K1 into capital W. Okay, this is not a small w, this is a capital W into R, where R is already shown in this figure. Okay, you can see this is the R, that is the effective radius. Okay, similarly the maximum positive bending moment can be calculated using the second expression which is given over here. This is K2 into W into R. Another is the maximum torsional moment, that is T, can be calculated by simple expression K3 into W into R, where all the values K1, K2, K3 has to be taken from a table. Capital W is the total load and R is the effective radius. Okay, so here there is one more term called as theta. Okay, so this theta is nothing but the angle between two supports. So in this case this is 8 columns, so theta value will be 45. In our case it is supported by 6, so we have total 360 divided by 6, so the theta angle in our case it will be 60 degrees. Okay, so now with this background let us go for the calculations. So this is a table which shows the coefficients K1, K2, K3 and the angle at which the maximum torsion is going to appear. You have to remember these values, especially the values for column number 6 and column number 8, because in the examination these coefficients may be given, may not be given. Very rarely we are using 4 column support system for circular beam. 4 column है बहुत कम होता है, ठीक है? And beyond 8, if the span or the radius is very high, in that case you have to go for more number of columns. Okay, so just remember the values for 6 and 8, and for 6 the angle is 60 degree theta angle, and for 8 it is 45 degree. K1, K2, K3 coefficients are there in front of you, and at the end you will also find a angle at which you will find the maximum torsion. Okay, so we are going to take the coefficients from this particular table. Okay, so K1 is 0.148, K2 is 0.075 and K3 is 0.0050. Okay, so this value we are taking. With this, now let us calculate the maximum bending moments. Okay, so K1, so K1 is 0.0148. So let me write down over here, this is 0.0148, and capital W. So capital W we have already calculated as 264.15. Okay, so this is 264.15, and the R. Okay, so R value we have already calculated. So R is the effective radius. Okay, so effective radius I think it is 6.2 divided by 2, that is nothing but 3.1. Okay, so this is nothing but 3.1. Okay, how much is this value then? maximum negative bending moment which will be occurring exactly above the support. बताओ. Yes. Sorry. 12 point. Someone cross check. बराबर. So this value is 12.12 kilonewton meter. बराबर है. So similarly, now we have to go for the maximum positive bending moment which will be occurring at the midspan, and its coefficient is 0.0075. So this value 0.0075. How much is this? Definitely it will be less than the maximum negative bending moment. 6.14 kilonewton meter. Okay. So you see the negative bending moment is magnitude is more and the positive is less. So definitely while designing the beam, okay, I'm not talking about the reinforcement, but while designing the beam we have to define the depth. So depth of the beam has to be decided based on the maximum value, whether it is negative or whether it is positive, it doesn't matter. Okay. So for this purpose we are taking, for calculation of the depth, we are taking the maximum value of the bending moment, that is 12.12 kilonewton meter. Okay. Apart from this we have to calculate the maximum torsion. So maximum torsion can be calculated as K3 into W into R, where K3 is 0.0015. Okay. So this value is 0.0015. How much is this value then? Maximum torsional moment. Sorry, 1 point. It's very less. Kilonewton meter. Okay. And then we have to calculate the shear force also. Okay. So now for the shear force, what we have over here is, this is the UDL. Okay. And this UDL, I think it is, we have already calculated the value of UDL. This is 13.56, isn't it? So this is 13.56, and the distance between two consecutive supports, I think it is 3.24, है ना? So this is 3. So whatever is the total load, half will go over here and half will go on this side. Okay. So your shear force is nothing but span divided by 2 multiplied by W. So where this W value is 13.56 and the span is 3.24. How much is the shear force now? Yes. Sorry, 22. ठीक है, 22 ले लेते हैं. ठीक है. So let us take, this is 22 kilonewton. Okay. So now for designing purpose, like I said earlier, we have to take the maximum bending moment. So maximum bending moment is 12.12 equals to QBD square. Okay. So here, so if I expand this expression, this is 12.12 into 10 to the power 6 equals to Q. What was the value of Q we have taken earlier? That is 1.527, isn't it? So this is 1.527 into width. So width of the beam, we are taking this as 200 mm. Okay. And depth of the beam now we have to calculate. Okay. So if you solve this expression, you are going to get the depth of the, or rather the effective depth of the beam which is required. Can someone tell me the value, please? Sorry? 199. This is mm. Okay, so you see we have assumed the depth of beam as 400 mm, but the effective depth required is 199. Okay, so if you want, you can revise this and do it one more time. Okay, otherwise you can continue. Okay, so let us continue for the time being. So if you go with this, so the effective depth will be, this will be 199.21. Clear cover or effective cover, you can take this as 25. So this is coming out to be roughly 225 millimeter. And what exactly we have provided, that is the total depth as 400 mm. Okay, so final depth we can take this as 400 mm if it is required. So let us take the depth as 400 mm. कि कम करना है, बताओ कम करें इसको? 400 ही लेते हैं, मैंने आगे का 400 ही किया हुआ है. ठीक है, सो द इफेक्टिव डेप्थ विल बी समथिंग लाइक दिस विल बी 375 mm. ओके, okay, shall I continue? So the depth calculations are done. Okay, then we have to calculate the AST. For calculation of AST, expression is very simple: maximum bending moment divided by sigma ST into J into D. So now we have to calculate the AST at two different locations, because we have two different bending moments. One is above the support and one is at the mid span. Okay, we also have a section which is having the maximum torsion. Okay, we have to design that one also, but for the time being we are skipping this because the torsional value is very less. Okay, even if you design, it will be safe. So that part we will cover in the design of instant. Okay, so for the time being, let us go for the reinforcement at the top. So for top reinforcement, the maximum negative bending moment is coming out to be 12.12. So what will happen, this value is nothing but 12.12, and the bottom value is 6.14. Okay, so sigma st is basically 130. Okay, j की वैल्यू कितनी है? I think 0.86. Okay, कहाँ गया? हाँ, this is 0.86 and the depth value is 375. How much is this AST and how much is this AST? Both AST, please tell me. हाँ बताओ, AST negative, reinforcement at the top 289 and AST at the bottom उसका roughly आधा आएगा 146. Okay, you can use IS 456 to calculate the minimum AST in beams. Okay, so as per IS 456, it should be either 0.15% of the cross section area or 0.85 FY BD. Both way you can do it. Can you tell me the values, please? Meanwhile, please answer your attendance. Yes, roll number 1, 2, 3, 4.
Present, sir.
Okay, 5, 6, 7. Aniket, 8.
Present, sir.
Okay, 9. Ketan, 10. 11. Mohit, 12. 13. 14, 15, 16, 17, 18. ओके, सो हाउ मच इज एएसटी मिनिमम? ये पहले वाले क्लॉज के हिसाब से कितना आ रहा है? 120, बहुत कम है। और ये कितना है? 153, बराबर है। एफ वाई कितना लिया? नहीं, अच्छा आई एस 456 ले रहे हो ना? हाँ, बराबर है। सो व्हेन यू आर यूजिंग आई एस 456, दिस विल बी 415. Okay, if you are using IS 3370, this clause is not there in IS 3370. So this clause is there in IS 456, so we have to use the FI for IS 456 only. Okay, so anyway, so you can see the minimum reinforcement which we have to provide is at least 153 millimeter square. So this is slightly less. Okay, so this can be 153, and this you have to provide as it is. Okay, so now ओके, सो नाउ कहाँ गया भाई? हाँ, सो फॉर दिस टॉप reinforcement 289, so you can provide I think two numbers of 12 mm die bars. How much is the area? कैलकुलेट करो। टू नंबर्स कितना आ रहा है? तो इसको बढ़ा दो फिर, 289 की जगह कितना आना चाहिए? सॉरी बाय मिस्टेक, ये सपोर्ट का ये वाला है। ओके, सो दिस इज two numbers of 12 mm die bars plus one bar of 10 mm die. I think this is going to solve the purpose. ठीक है, बराबर है। And here, so this is the total reinforcement which we have to provide at the top, and this is the reinforcement which we have to provide at the bottom, that is two bars of 12 mm die. I think this is going to solve the purpose. Okay, and as far as stirrups are concerned, you can use IS 456, and base whatever minimum shear reinforcement is required, accordingly you have to design the stirrups. Okay, so I'm not going into much details for that. You have to go for shear check also. So shear check has to be done, and we have already calculated the shear force value as 22 kilonewtons. Barabar hai? So here this is 22 kilonewtons. Okay, so the shear force or the shear stress is 22 divided by B is 200 mm multiplied by effective depth is 375. How much is the shear stress? कितना आ रहा है? रीजनेबल ही आएगा वैसे। जीरो पॉइंट टू 0.29. Okay, so this is 0.29 newtons per mm square. Okay, now you see this maximum shear is occurring near the support. Okay, so near the support, whatever AST you have provided, that you have to consider over here while calculating the PT. Okay, so if you remember, at the support we have provided two bars of 12 mm die bars plus one bar of 10 mm die bar. Okay, so accordingly you calculate percentage of steel. हाँ, कितना आ रहा है पीटी? यस, एनीबडी? 0.% Someone please cross check. ये करके बताओ. This is 100 divided by B. B is 200. Depth is 375. Okay. AST is pi by 4 into first is 10 square plus pi by 4 into 12 square multiplied by 2 because we have taken 2 bars. See here you can see there are 2 bars of 12 mm dia bars plus 1 bar of 10 mm dia. How much is this now? Sorry, 0. Percent. Okay. So accordingly, you have to refer IS 3370 and you have to calculate the value of tau c. निकालो. है किसी के पास? ठीक है, कर लोगे ना? You refer that particular table, you get the value of tau c. Definitely, whatever value of tau b you are getting, it will be lesser than the tau c value. Okay, this I have already checked, so you don't have to worry. And if it is like this, that is tau v is lesser and tau c is more, you have to provide the nominal shear reinforcement. This is the expression, that is 0.87 fy ASV divided by 0.4 times b, and this accordingly you have to provide the spacing of 2 leg 8 mm dia bars. If it is not safe, in that case we have to go for the design of shear. Okay, design of shear you have already done, so I am not going into much details of that. Okay, so we will stop over here because in the next class we'll start the gantry. Okay, so please complete this and please make sure that you are drawing an appropriate figure. You are going to become a structural engineer now, तो ऐसे आड़े टेढ़े हाथ से मत बनाया करो, अच्छे से ड्राइंग बनाया करो. ठीक है, आई एम गोइंग टू डिडक्ट मार्क्स ऑन दैट. जिस दिन तुम्हारे मार्क्स कटेंगे ना तब शायद तुमको रियलाइज होगा. तो अभी से आदत डालो, अच्छे से ड्राइंग करोगे कर. ठीक है, ओके, just give me a moment. See, there is a company that is the Modern Arch. It is located in Nagpur IT Park. So I had discussion with the owner of that company. We are in touch since long back, and last year we are not able to accommodate the interns at his organization. But this year we are planning to send at least couple of students in his organization. So I'm just going to show you a technology on which they are working. It is called as Lethally Arch. Okay. So I'll show you the video. I don't know if there is some issue. Okay. But this will be a kind of a research internship. So there you won't be doing a typical uh, project like you have some bridge design and you will be doing some design and the design will be given to the client. So it's not like that. It's a pure research internship and it is mostly done on ANSYS and STAT. So if you are comfortable with ANSYS as well as STAT, then only you go there, otherwise don't go. Okay, I'm very point blank I'm telling you this. Okay, and they will be interviewing you. Okay, it's not like कि मैंने फोन करके बोल दिया और उन्होंने ले लिया. No, it doesn't work like that because it's a research kind of a thing. So those who are interested, please let me know. Okay, I'll tell all the names to the respective HR. They are going to call you for interview, and after interview, they are going to shortlist you for the internship. Okay. Now, just let me show you this Lethley arch. I don't know how many of you are knowing. किसी को पता है Lethley arch क्या होता है? Anybody? I'll just show you. I don't know, my PC is probably antivirus is working, so I hope this is visible. So see what they are doing is, so usually what happens is like this. See, generally what happens is you have to build a uh, bridge. Okay, तो ब्रिज में क्या होता है? देर आर टू थिंग्स. वन इज दैट ओल्ड वन, जहाँ पे आपको पूरा नीचे फॉर्मवर्क लगाना पड़ेगा, कंक्रीटिंग करना पड़ेगा, 7 दिन बाद 10 दिन बाद जो भी है कंक्रीटिंग फॉर्मवर्क निकालना पड़ेगा. तो इसके बीच में बहुत सारे प्रॉब्लम्स आते हैं. सो नाउ वी आर गोइंग फॉर प्री-स्ट्रेस काइंड ऑफ अ ब्रिज, बट प्री-स्ट्रेस पोस्ट टेंशन ब्रिजेस आर used for very long span. Okay, for shorter span, this kind of technologies nowadays it is gaining some popularity. Okay, I think voice is not there anyway. So here you see what they are doing is, can you see those small blocks? Okay, so it's wedge shaped block. Okay, so they are constructing this wedge shaped blocks in the factory. Okay, they are making a chain out of this. Okay, all those wedge shaped blocks are kept just in one line. They are putting a cable over there, and they are going to fix the cable, so that they are just lifting that thing. And once they are lifting, you will find the arch is formed. I think you can see the arch. Okay, so what they are doing is, everything is kind of a precast. It is fabricated in the yard, and then it is transported, and then it is simply kept over there with the help of art. So you can see these are the wedges. Okay, it is getting lifted, and then it is kept on the side. So after keeping, it becomes like this, and then rest of the portion is exactly same. And the load transfer mechanism is basically your arch action. So you can see this, see it is getting lifted. Okay, so in this picture you can see there is one old arch, and there is a new arch in the background. See, okay, एक पुराना वाला आर्च ब्रिज है और दूसरा वाला ये वाला. This is called as Lethley arch. So they have been working on this technology only. Okay, so you will be working on this particular project, and you will have to analyze the arches and bridges, all kind of loads. Okay, that may be IRC loading. Okay, and our traditional loadings. You have to design the bridges on STAD also, and we have to go for FE analysis using ANSYS also. ओके, सो यहाँ पर कमर्शियल ये नहीं है, अप्रोच नहीं है, इट्स अ प्योर रिसर्च वर्क. ओके, सो प्लीज, द कंपनी नेम इज मॉडर्न आर्ट्स. यू कैन सी एट द एंड देयर इज अ लोगो. ओके, सो दोज हु आर इंटरेस्टेड, जस्ट गूगल मॉडर्न आर्ट्स. ओके, सी व्हाट दे आर डूइंग. ओके, ये आज करो, तुम शांति से बैठ के करो. व्हाट दे आर डूइंग, व्हाट दे आर इनटू. ओके, उसमें तुम लोग को क्या क्या लगने वाला है, दैट आई हैव ऑलरेडी टोल्ड यू. One is the good knowledge of design of bridges. Okay, and the IRC loadings. तो ये अगर तुम्हारे फंडे क्लियर है तो ही मुझे शाम तक, कल तक बताओ कि यस सर आई एम इंटरेस्टेड, सो दैट आई विल फॉरवर्ड योर नेम टू दी HR. ठीक है, एंड योर इंटर्नशिप इज लाइक, क्लासेस तुम्हारे हैम्पर नहीं होंगे, because it's just a research internship, so you will be working on ANSYS and other things. So whenever it is required, you can come down to the college irrespective of your supervisor. किसी का आनंद सर है, किसी का पासपोर्ट सर है, जो भी है. So for project work you will be allowed to come to the college, and you can complete your project work also. Okay, so this is kind of opportunity which I am giving you, so please think accordingly. Let us finish this video first. You can see this is the placing. It's a rapid way of constructing bridges. You should also have good knowledge of concrete technology also. Okay, ये सारे हाई परफॉर्मेंस कंक्रीट के हैं. इट्स नॉट M25 और M50 और M40, थोड़े से ज़्यादा स्ट्रेंथ वाले. I think audio is not there anyway, but we can search on this. So this is how it is getting lifted. So the office of Modern Arch is located in IT Park. Okay, they have two companies. Just two names are there. One is Modern Arch and one is the Global Arch. काम दोनों एक ही करते हैं, ओनर भी एक ही है. They have some reasons to have two different companies, but they are working in the same area. So the main objective over here is to reduce the execution time. इससे सिर्फ उठाया डाल दिया, एक दिन में काम खत्म. And there are many projects going on in and around Nagpur. 200 किलोमीटर के रेंज में बहुत सारे प्रोजेक्ट्स हैं इनके पास. So if we wish, we can all visit on some of the projects, especially when the this type of execution work is going on, because यार्ड में जाके कंक्रीटिंग देखने में कोई मतलब नहीं है ना. That you can see in the lab also. Okay, so they have quite good company. So please think of this and let me know by today or tomorrow whenever. But इसको पहले देखोगे, हाँ, ऐसा नहीं कि as it is सर नहीं सर आई एम इंटरेस्टेड. इट्स नॉट लाइक दैट. ठीक है, पहले उसको सोचो समझो एंड वेदर यू आर कैपेबल इनफ टू वर्क ऑन स्टैट दिस एंड दैट, देन ओनली यू टेल. नहीं तो क्या होगा, वहाँ पे बेइज्जत होके वापस आओगे. ट्रस्ट मी, वहाँ पर मैंने दो चार बच्चे भेज चुका हूँ, एक को भी सिलेक्ट नहीं किया उन्होंने, ना प्लेसमेंट के लिए ना इंटर्नशिप के लिए. ओके, सो प्लीज बी प्रिपेयर्ड, देन ओनली टेल. ठीक है, चलो. सो आई थिंक वी कैन स्टॉप नाउ. ओके, ऑनलाइन स्टूडेंट्स